Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced Euler's formula, which allowed us to write complex numbers in this exponential form. And in this video what I want to do is I want to talk about how we might go about now solving what are known as complex polynomials. So these are going to be polynomials with complex coefficients. So let me talk about this by going over to the tablet, and I'll title this something like complex roots. So we've already seen how to find roots to quadratic equations with real coefficients. So that was things like x squared or ax squared plus bx plus c. So what do I mean when I talk about a complex polynomial? So a complex polynomial I'll say of order n. N here is a natural number. Is of the form, we'll write it as z to the power of n, and we'll put maybe a number in front here. We can write that as a to the n plus a to the n minus 1, z to the n minus 1, going all the way up to a0 equals, and we'll make it equal to 0. So we've got a complex polynomial of this form. And here, each of the a's is in C. Namely, they're complex coefficients, or they're complex numbers, from running from 0 up to n. Okay, now we might say, well, how do we solve these? And do these things have solutions? And do these things do have solutions? They have solutions in the complex numbers. However, much like in real analysis or with real polynomials, these things are extremely difficult to solve in general, right? In fact, right, I mean, you know how to solve quadratic equations with real polynomials, but kind of anything beyond that, like cubics and quartics, is rather difficult. So that's going to be much like the case here. We can't write general ways of solving complex polynomials. That's rather tricky to do, and some people even are doing research on that. But let's specifically look at just a polynomial of the form where I kind of remove all these terms and I simply just have this thing here with an equaling 1 effectively equals to a complex number. So in other words, I just take this a0 to the other side. So that is, I can define, so I can construct a definition now. And we can say the nth root, let's maybe put this in a different color. Of a complex number z, we can write it as z, is a complex number w such that the following equation is satisfied. We're going to have here w to the power of n is going to equal z. So we're saying that the nth root of this complex number is w. If I can take that complex number w, raise it to the power of n, and that equals z. So that's what I mean by an nth root. It's one in which when I raise it to that power, it gets me back to where I start. And I think I may have in the notes used the w and z the other way around, but it doesn't really matter in this situation. So this drives kind of a different definition, or let's first look at another definition of when I look at the particular case when this number on the right hand side is simply 1. And this drives a definition known as a root of unity. So let z be a complex number. Then z is and we'll call it a root of unity. Root of unity if z to the power of n equals 1. And in particular, maybe we can specify this in more detail. We can say this is an nth root of unity. So we're claiming that if we have a complex number and we raise it to the power of n, where n here is some kind of natural number, if that equals 1, then that is an nth root of unity. But if in general we can just say that if we've got a complex number, that if we raise it to the power of n and it equals 1, we just call it a root of unity. Now, how would we go about solving this equation? How would we go about solving this? Well, that's okay, it's obvious. There's an obvious solution, z equals 1. Clearly 1 to the power of n, where n is a natural number, is simply just 1. So clearly we can see 1 is a solution. But much like even when I talk about real polynomials, I can have multiple solutions to polynomial equations, right? For example, I could take x squared equals 1. Well, that implies x equals 1 or x equals minus 1. Right, that's an example that I've got a single polynomial equation and there are two solutions that I can find to these equations. So whilst I found one solution, that doesn't necessarily tell me that I found all the solutions. What are all the solutions to this? And in fact, it turns out there are going to be n many solutions to this equation. And the way in which we can think about that is we can think, well, all these points, by definition, must lie on a unit circle, right? If I take the modulus of this thing, so we have the modulus of z to the n is going to equal the modulus of 1, which is going to equal, in other words, it's saying the modulus of z to the power of n equals 1, right? Which in other words is telling us that mod z is equal to 1. So all of these complex numbers, all the solutions to these equations must lie on the unit circle within the complex plane. And if we just think about what the property they must satisfy is, if they lie on this unit circle, they must have the property that when I multiply them by themselves n many times, that takes me back to the point 1. And if I think about, again, how multiplication works on the complex plane, multiplication stretches that vector by the modulus, but in this case it's 1, so it doesn't do any stretching. And it rotates it by the arguments. All that happens by multiplying z multiple times is just constantly rotating it by the argument of z each time. So in other words, what I get is n times by theta, where theta is the argument of z. So if I think about this, maybe drawing a picture here that might be useful. I've got that everything must lie on my unit circle. Let's see if I can draw a unit circle in here. This point is the point 1. So I know that one of my solutions is indeed this point 1 here. And the other solution, what would be another solution? Well, another solution must be one that is 2 pi divided by n into this complex plane. Why is that the case? Well, if I'm going round the full radius or the full circle here, that has angle 2 pi. And I've got to have the property that when I raise it to the power of n, I should get back to 1. In other words, I should get back all the way around the circle. So if this number here was z, then z squared would kind of take me to here, and z cubed would take me to here, and z to the 4 would take me to here, and I see that it kind of takes me all the way around, and I see that what I get for z to the power of n, so then z to the n, is going to have argument, so we can write this as the argument of z to the n is simply going to be 2 pi. In other words, it's going to lie on the positive real part of the complex plane. It's going to lie somewhere here. But we also know its modulus must equal 1. So in other words, it equals 1. So we've got here that z to the power of n equals 1. And in turn, we can figure out what all the other complex solutions are, because all the other complex solutions are simply just going to be given by the other points. Right? It's going to be given by z squared, z cubed, z to the 4, and kind of going all the way around of z to the n minus 1. In other words, I find that I get n many solutions. I've got 1, 2, I go around, I've got n many solutions to the equation z to the power of m equals 1. So there are n many roots of unity to a polynomial that's of the form z to the power of n equals 1 in the complex plane. And we see, in fact, that there's a nice relation to geometry here, that what shape do our complex numbers form around, so where, what shape do our complex numbers form around the complex plane? If we take our complex numbers and make these the vertices of a polygon, we see that what it forms is it forms a regular n-sided polygon inscribed within a circle of radius 1. So in fact, we can figure out that there's some relationship here between the geometry of polygons and the solutions to polynomial equations of the form z to the n equals 1 and roots of unity. So what's our claim now and what's our theorem? So hopefully we've kind of motivated that with some geometry, but our theorem is going to say something like the following. So let z, we can write it as, instead, let's say, write it as we've done in the notes. Suppose that z to the power of n equals w, with w in the complex numbers, and we'll take n to be a natural number. Then the set of nth roots of w is given by what? Which is given by all those points around this circle that I've got, but now because I've taken that this is not a complex number that necessarily has modulus 1, it's going to be now a circle that has radius whatever the modulus of w is. So it kind of spreads around a circle of whatever the radius of modulus of w. So in other words, my solution set is going to be given by, I write it as S, is going to be the set of elements w, or the modulus of w to the power of 1 over m, e to the I, theta plus 2 pi k over n, such that we take k running from 0 up to n minus 1. So that kind of gives us all these points around our circle. I think I said before, actually, the unit circle, or the circle now is not a radius modulus of w, sorry, it's got radius, the modulus of w, kind of the nth root of the modulus of w, that's what its radius is. And then the points are scattered around these kind of equal angles of theta around that circle. Okay, so let's see if we can find an example here. We've got an example that we've got in the notes. And discuss how we would do that. So example. Let's take z to the power of 4 is equal to minus 1 minus root 3i. So we know that that lies, if we draw our picture, once again, this is the imaginary part, this is the real part, and this lies somewhere down here. This is 1, this is root 3. And we've already seen that this angle here was pi over 6. And the total angle was minus 2 pi over 3. So we can write z to the 4 as equal to what is going to equal to 2e to the minus 2 pi I over 3. We've already seen that we can write it in that form, because again the modulus here is 2, because we take 1 plus root 3 all squared, square rooted. So what is our solution set, or what is our set of roots to this equation? So then the fourth roots of minus 1 minus root 3i are given by the elements of the set. So I basically take the set, I take a circle that has now the radius of the, whatever the nth power here is, the nth root of 2, so it's going to be 2 to the power of a quarter, It's going to be taking my circle down to a radius of 1/4, centered around the origin. And then I just want to equally space my roots around where it's going to be split around now of 2 pi over 4. So in other words, I get that I've got e to the minus 2 pi I over 3 plus 2I k pi, and then that whole thing is going to be divided by 4. So maybe I'll shift that up slightly so you know that's raised in the power. Everything there is in the power. So that is our solution set now, right? And we just want to define where k is. So k here is running from 0, 1, 2, and 3. Which is exactly our 4 solutions, right? So we get our first solution, our second solution, our third, and our fourth solution corresponds to 4 different values of k there. So indeed, this polynomial, which has degree 4, has 4 solutions. Okay, so that's where we're going to conclude the video. And in the last video on complex numbers, what we're going to do is we're going to look at how to solve quadratic complex polynomials, much like how we can solve quadratic real polynomials that you've seen before using the quadratic formula. So again, as always, I remind you to read the notes after this and attempt any problems in the module handbook pertaining to the material that was covered here. So thanks very much for watching, and see you in the next video.